So, hello everyone, and welcome back to the good stuff we have been doing. Today, I'm here in this video to tell you and convince you that you have to master your trig identities. They are very, very important. And why do I say that? Well, here's a beautiful integral before us. The integral from 0 to 1 of tan inverse of x plus square root of 1 plus s squared divided by 1 plus s dx. And we need to evaluate this integral in closed form. Now, the standard substitution is clear to everyone, which is that x equals to tan theta, the so-called Weierstrass substitution. This is one that everybody thinks of when you look at it because of the fact that the square root of 1 plus x squared becomes 1 plus tan squared theta, and this we know is square root of secant squared theta, and this will be just secant of theta because x runs from 0 to 1 and theta will run from 0 to pi over 4, so it will always be positive, so we take the positive square root. So this would be a secant of theta. Then if we apply this substitution here, you end up with having to deal with the integral from 0 to, then you have a pi over 4, point being that when x is 1, theta will be pi over 4, and this will be tan inverse of, then you have a tan of theta, and then you have to deal with secant of theta, all divided by what? 1 plus tan of theta. Then you have a secant squared theta, the theta, because dx here, for this our case here, dx would be secant squared theta d theta. Now, okay, so we have been able to get rid of the square root. Then how do we now deal with this tan theta plus secant theta? And that is where the title of this video comes in play, because we are trying to tell you that you can't do integration without mastering your trigonometric identities. That is impossible. It's not possible. There's no way. You have to master it. You have to know every identity. Not every, but you have to know the basic ones. The basic one being the half angle formula, double angle formulas, addition formulas. Maybe the sum to products can be useful, but because it's something that you can easily derive without stress, so I don't think anybody ever tries to memorize it. I know it sometimes I don't know it. Sometimes I remember it, sometimes I forget it, but anytime I forget it, I can easily derive it within less than a minute. So what is the purpose of memorizing it? But for other identities, you have to know them by heart. Not just if you memorize them, you have to know them and know how to use them. So, and that is what we're going to do here. We're going to write this as the integral from 0 to pi over 4. Okay, then here you have a tan inverse. Okay, this is, write this as sine theta over cosine theta. And then the second part, you write this as 1 over cosine theta, where then you would have 1 plus what? Okay, let's just put this as 1 plus tan theta secant squared theta d theta. Of course, we can maybe write this as 1 over cosine squared theta and probably bring a cosine squared theta here. But the problem is that we'll be needing them in this form, as you shall soon see. When I solved this problem by paper, I did require them. So if you go further from here, you get the integral from 0 to pi over 4. So still you have a tan inverse. And then you have a, at the top you have a 1 plus sine theta, because the denominators are the same. But this, we could write this one as cosine squared theta over 2 plus sine squared theta over 2. Again, your trig identity, which says that sine squared x plus cosine squared x equals 1. Then on this part, you can have this as twice of sine theta divided by 2 cosine of theta divided by 2. Again, this time around we use the double angle formula, whereby sine of 2 theta is twice of sine theta cosine theta, and everything is divided by, now instead of writing cosine theta, we can write this as cosine squared theta over 2 minus sine squared theta over 2. Again, this is the addition formula, so this will be cosine squared theta over 2 minus sine squared theta over 2, and everything is divided by what? Just 1 plus tan theta. And then here we still write secant squared theta d theta. This may look like Okay, let's simplify, but you don't have to. Me, I simplified it while solving it, but when I got to the middle part of the work, I realized that I don't have to simplify it. So let's see. Then this would be equal to, let's get the black. This right here will be equal to 0 to pi over 4. Then you have a tan inverse, and notice that here we could write this as cosine theta over 2 plus sine theta over 2 all squared. Then at the bottom we could write this as cosine of theta over 2 minus sine of theta over 2, and then multiply by cosine of theta over 2 minus sine of theta over 2. So everything is going to be under a bracket, and you would have a 1 plus tan theta secant square theta d theta. So if then you put this as 0 to pi over 4, then notice that over here, this one of this expression cancel the bottom part. This is a plus sign, of course. So you would have just a tan inverse of what? Cosine of theta over 2 plus sine of theta divided by 2, all divided by cosine of theta divided by 2 minus sine of theta divided by 2. Just making sure that everything is the 1 plus tan theta. Then you have secant square theta d theta. So we're making some good progress here. Next up, what do we do here? Well, you still have to put this as integral from 0 to pi over 4. Then if you divide top and bottom by cosine, you will have this is a tan inverse of 1 plus tan of theta over 2. And this is 1 minus tan theta divided by 2, and all divided by 1 plus tan of theta secant square theta d theta. And if you remember your trig identities, again you see everything here is boiling down to trig identities. If you remember that tan of a plus b is equals to tan a plus tan of b divided by 1 minus tan a tan b. So if you remember this identity, you will come back and say, okay, let's look at this part. You can see that this tan of pi over 2 plus theta over 2 would be equals to, sorry, pi over 4. Tan pi over 4 is 1, so you have a 1 plus tan pi over 2 all divided by tan pi over 4, which is 1 minus tan pi over 4 is 1, so you have tan theta over 2. So you see that this whole expression can be replaced by just tan of something. So you see, the trig identities keep haunting us, which is why I told you that this integral is going to convince you to love trig identities. So you come back and you have the integral from 0 to pi over 4 of the tan inverse of the tan of what? Pi over 4 plus theta divided by 2, all divided by what? 1 plus tan of theta secant square theta d theta. So again, we're making some good progress. This will be integral from 0 to pi over 4. And now finally, we could write this as pi over 4, then plus theta over 2 divided by what? 1 plus tan of theta secant square theta d theta. And we have used the fact that tan inverse of tan of x is equals to x, although there are restrictions, especially when x is bigger than pi. Okay, there are restrictions, but we don't really have to worry about such things here because our integral is from 0 to pi over 4, and the argument, of course, is less than pi. So we don't have to worry about whether it is pi minus this or what, or pi, like pi minus x or pi plus x or whatever, because we're not crossing that threshold yet. So, but here now we could take u to be, or let's say we take t to be tan theta, and notice that the t will be secant square theta, something I told you about that we'll be needing, as you progress. So this is 1 plus t dt. Then what about here? This is the integral from 0 to 1, of course, of pi over 4 plus half of tan inverse of x, all divided by 1 plus x dx. So you see, now, although to be honest with you, this is not the simplest integral of all time, but it's, if we can zoom back, if we can zoom it out a little, you can see we have come a very long way from this. Let me just even zoom everything. You can see that we started up from this a little bit more complicated expression, and let me use a different color entirely. So we started off from this expression here, and now we are over here. So this, we can demarcate it even, and let's just continue in this fashion. But you can see that everything here is by trig identities. Now let's finish off the problem and congratulate ourselves, because it's not easy to solve all this problem, but we are doing a good job. So this will be pi over 4 of the integral from 0 to 1 of 1 over 1 plus x dx, which is simple. The only one that is going to give us an issue is this one, where you have a half the integral from 0 to 1 of tan inverse of x, all divided by 1 plus x dx. And this is the so-called sqrt integral. This integral equal pi over 8 log 2, I believe. Should be equal to pi over 8 log 2. Well, we're going to deal with this integral, but let's just take this. So this will be pi over 4. Then this will be logarithm of 1 plus x from 0 to 1, and this will be plus 1 over 2 times what? Pi over 8 log 2. Now, if you go further, you will have pi over 4 log 2 plus what? Pi over 16 log 2. So to get 16 here, you need to multiply 4. So 4. So you have 5 pi over 16 log 2. I think, yeah, that's the answer. 5 pi over 16 log 2. That is the correct answer. So which means that I'm right. We are not the answer because I solved this problem. Now, how do we worry about? Okay, I made a video about this sqrt integral. You can check the description. But for the sake of completeness, I will use a different method. In the video I made, I used the fact that tan inverse of s could be used to be represented as the integral from 0 to x of 0 to 1 of x over 1 plus x squared t squared dt. I use this fact that this is the formula for tan inverse of x. Now I use a double integral method. I think I did this, but I will present a different solution here. So let's share the solution. Thank you. It's very lovely. What we'll do is that we're going to write this integral from 0 to 1 of tan inverse of x, all divided by 1 plus x dx. We're going to write it in 2 parts. So we're going to put a half. So this will be, okay, no, we're going to put it to, wait. Oh yes, we're going to write a half times what? The integral from 0 to 1 of tan inverse of x, all divided by 1 plus x dx. And then we also have to write integral from 0 to 1 of tan inverse of x, all divided by 1 plus x dx. Okay, so notice that these integrals are the same, so this is valid. Now we're not going to touch the first one. We just have to write a half integral from 0 to 1 of tan inverse of x, all divided by 1 plus x dx. The second one, we are going to write integral from 0 to 1. Then we are going to take x. They call Morbius transformation. You take x to be 1 minus t over 1 plus t. If you do that, notice that when t here become 1 minus x over 1 plus x. So when x is 0, t is 1, and when x is 1, t becomes 0. And also dt will be negative 2 over dx over 1 plus x all squared. And also 1 plus x, let's see, go back. 1 plus x would be 2 divided by 1 plus 2 divided by 1 plus t, right? Yeah, so we have 2 divided by 1 plus t. So if we come back here, and then let me put it, zoom that, yes. So if we come back here, you will have the integral from, let's say, from 1 to 0, then you have tan inverse of what? Tan inverse of 1 minus t over 1 plus t, all divided by, now the bottom part, I think we already concluded that 1 plus s is 2 over 1 plus t, because, yes, so you have 2 divided by 1 plus t, so you have negative 2 dt over 1 plus t all squared. Okay, and also don't forget that we're going to have to borrow a simple fact that tan inverse of 1 minus t all divided by 1 plus t is going to be pi over 4 minus tan inverse of t, which is even why we did this substitution. So if we borrow this fact, which also can easily be proved, you would end up with, let's use this color. This is half the integral from 0 to 1 of what? Tan inverse of x all divided by 1 plus x dx. Why on this other hand? So the negative and negative, this will become a positive. So you have the integral from 0 to 1. Now this is going to be pi over 4 minus tan inverse of x all divided by, here you get 1 plus t cancel out, 1 plus t, you get a 1 plus t dt. Sorry, 1 plus x dx, right? Okay, so notice that this integral now and this other integral will cancel out. Okay, so we are left with half of the integral from 0 to 1 of pi over 4 divided by 1 plus x dx, which is pi over 8 times the integral from 0 to 1 of 1 over 1 plus x dx, and then which is pi over 8 times integral times the logarithm of 1 plus x as we run from 0 to 1, and which is going to be pi over 8 log 2, which is, that is because it's called sqrt integral. It's called sqrt integral, and it is well known. Of course, you have to know it, but I have not derived this via this method before. Okay, I did, the one I derived was the fact that you can write tan, I'll just show you the snapshot. You can just check the description, you're going to see it. Integral from 0 to 1 of tan inverse of x over 1 plus x dx is integral from 0 to 1 of 1 over 1 plus x times what? The integral from 0 to 1 of x over 1 plus x squared t dt, then you have a dx. So this will be the integral from 0 to 1 times the integral from 0 to 1 of x over 1 plus x, so 1 plus x squared t. So this is, you can continue from here, dt dx. You can put this in partial fraction and you can do something from there and good things will happen. So that is that. So thank you very much for watching, and I hope that in this video I'll be able to convince you and not confuse you that trigonometric identities are one of the, like the heartbeat of calculus, and you should master them and know them by heart. So thank you very much for watching, and please subscribe to the channel, please. Thank you very much.